In this video, we are going to discuss about an important tool in mathematics that we use in physics as well, that is the Taylor series, and we'll be taking the physical cases that are involved in the Taylor series. To start with, as you can see on the screen, you have four plots over there that I've made for you. They are showing the variation of the position with respect to the time. Now in the plot A that you see, the first one, we have the variation as a constant value, that is the position does not change with time. It was x naught at t is equal to 0, and it remains even as time progresses, which is represented by this equation that we have considered, the first equation, that is x naught is equal to x naught or x at 0. So this is what we have observed. And as far as the second graph is concerned, the position changes, but it changes constantly with respect to time, which means it covers equal distances, or it changes position equally in equal intervals of time. And as a result of that, we have a constant velocity, or we can say a constant speed in that case, and the resulting equation from that observation that we have over there is going to give us x is equal to x naught, which is the initial position, plus the position that it has taken in a time t, moving with a constant velocity v naught. So x naught was its initial speed, initial position. So from that initial position, it has now moved over to a new position, because the new position was moved or reached with a constant velocity v naught. So we have v naught times of t. We can assume the scalar case where we are considering the v naught as the speed. Now equation, because the velocity or the speed remains constant at every instant of time in that case that we are considering right now. So we have v naught to be equal to dx over dt, which is the first order derivative of the position at any given instant of time, and then we can set the time to 0. Why do we need to set the time to 0? Because we can consider the interval for time tending to 0, and we can just obtain the value v naught from that. You can do the derivative of that term. So if we get dx over dt, then x naught being a constant term vanishes with the derivative, and dv naught over dv, the v naught is constant as well, because we have provided the same data. So v naught goes outside, dt over dt goes to 1, and as a result of that, we have this to be equal to just v naught. Even if we set the time to 0 or anything, the first order derivative is definitely going to give us v naught. While as far as the second order derivative is concerned, we will obtain the acceleration, which is the case, because in this case we didn't have any acceleration, which is the figure B. But as we move towards the case C, we have the equation as follows. Not only does the position change with respect to time, but also this also represents an accelerated motion. Now an accelerated motion has the position changing exponentially in higher powers of time, especially for a constant acceleration that we are considering over here. The time, the x coordinate changes to a maximum second power of the time, that is t squared. And that is why, because the acceleration has to be constant in this case, so the double derivative of that entire equation that we see, that the equation C over there, the entire equation double derivative or second order derivative of that is going to yield a naught, the value, that is the acceleration. Now consider the case of variable acceleration in the figure D. In that case, you may have higher powers of time, and as a result of that, there will be some constant multiplied to every time every power of time. So just for example, we start off with x naught multiplied to t to the power 0 because that is 1, then followed by v naught, which is again a term, and that is multiplied to t to the power 1. We have half a naught, which is again another term. We take it as c2. Suppose c naught, c1, c2, we give them numbers, we give them specific coefficient values. They are the coefficient of the power terms of time. And then we can take any other term which we consider k at the top, or we can take that as c3. And likewise we can proceed, because we do not know that at what power of time exactly this ends. We can in general consider an infinite series where x is equal to some coefficient multiplied with some power of time, and the corresponding terms are a summation of this entire case, where Cn t raised to the power n is summed over from, it can be summed over from 0 to infinity. Again, it may end anywhere between that, but we, for general case, we can consider that kind of a summation. Now this tells us about the variable acceleration case. Now with this mathematical approach to our physical problem that we see at hand, we can now enter into the field of explanation related to the Taylor series. Now before that, in general, if we were to obtain some coefficient of, say, this value Cm, which is the coefficient of t raised to the power m, then the coefficient Cm can be determined, as was in the case of these two terms, that is v naught and a naught, which were the coefficients of t and t squared. As you can see, v naught was determined by the first order derivative because it was multiplied to the first power of t, and a naught was obtained by taking the second order derivative of the equation, because a naught was multiplied to the second power of t, that is t raised to the power 2. So similarly, we can say that Cm will be the coefficient of some t to the power m term, and therefore the coefficient Cm can be determined by differentiating the summation m times. We have to differentiate it m times, because as you can see, twice differentiated, you have the result for a naught because it was multiplied to t squared, and because v naught was multiplied to t, you just have to take the first order differentiation. So m times differentiated with respect to t by evaluating the result at t is equal to 0. Why t is equal to 0? Now you can know why t is equal to 0, because there will be some m plus 1 term which will be containing the t, and we have to set that to 0 in order to get that value of Cm. For example, if I am to consider this particular equation over here, we know that we have the higher powers of t over here, but I want to determine the value of C2. So in order to do that, I'll just take the second order derivative of x with respect to t, and as a result of that, and then also I'll have to set t is equal to 0. Then what happens is that the first term vanishes in the first derivative itself, the second term then vanishes after the second derivative, while the third term will contain 2 times of C2, and that's all, because after the second derivative the t term will go away. But what about the third term? Well, in the third term we have the case of the first derivative resulting in a 3, then the second derivative resulting in a 2, and then in the third derivative we have c3, but we still have a t over there. And similarly, in the next case we'll be having 4, 3, 2, and then we'll be having c4 and t squared multiplied to that. If you have written that and tried doing the derivative of it, then you will get to know it in a better way. Now, in order to obtain, so with t is equal to 0, what we have is these terms will vanish to 0 because they will be containing the t, and they will vanish to 0, and all that we'll be having is c2. Well, it is 2 times of c2, but that 2 can be divided or taken to the other side, and we will just be obtaining the value of c2. This sure is a correct method to determine the value. So in general, if we are obtaining Cm, I'll be taking it over to the next page and you can check for yourself. It's quite easy, having known the pattern that we have studied so far. What we get from that is Cm will therefore be equal to 1 over m factorial, the mth order derivative of x with respect to t at x is equal to 0. This is a way of writing it at x is equal to 0, but if you have any other kind of notation, then it's fine. So we are taking this, sorry, it's actually t is equal to 0, not x is equal to 0. When the differentiation is with respect to t, we have to set t is equal to 0 rather than x is equal to 0. If the differentiation was with respect to some other value, then we would have had to set that to 0. Now, this, as you can see, if we would have, let me go back to the previous page. Now, if you were to determine C3, then you would have taken the third derivative, and in the third derivative what you would have had as the coefficients is 3, 2 and 1 multiplied to C3. And when we would evaluate the value of C3, all three of them, 3 multiplied to 2 multiplied to 1, which is in fact 3 factorial, would have got divided to the other side, which is exactly the case that I have mentioned over in the next page. That is the m factorial term, which is m times of m minus 1 times of m minus 2 and so on up to 1, that being the coefficient of Cm after differentiating it m times, then that comes down to the other side. So it's pretty clear from this case that how we are obtaining the coefficient values. Now the Taylor series, it describes any given function. Now we'll know that how this Taylor series is so beneficial to us. It can describe any given function as follows. The Taylor series describes a function, let us say fx, as fx is equal to the summation of Cn x raised to the power n, n taken from 0 to infinity. So this is an infinite series that we are considering over here, and where we have the value of Cn to be equal to 1 over n factorial, the nth order derivative of the given function with respect to the term which is varying. So with respect to x in this case, where with respect to x, because it is depending on x, not varying, but it is with respect to the independent term on which the given function is dependent, and then setting that independent term to 0 because we have to exclude the higher orders as well. So with this we can just extend or expand this series. So fx will simply be equal to f naught, the first term where we have C naught. Well, C naught in that case will be equal to 1 every time, because is 1 over 1 factorial, and the nth order derivative in that case is going to give us the first term itself. So this is F naught. C naught is 1. So we have F naught plus x over the first 1 factorial. The first derivative of x, we are taking it as f primed x and then setting x to 0, plus x squared over 2 factorial. Remember, these are the values of Cn that we are providing. Double derivative of f with respect to x and setting x to 0. Then again x cube over 3 factorial. Third order derivative and then setting it to 0, and it continues up to infinity. Now let's take a few examples for our understanding. In the first example, we set the value of fx, a given function, as the sine of x. So in that, in order to expand that, we'll be taking the same case over here, that is f of 0, which is the first value, that is over here, f of 0, which is in this case going to be sine 0. So sine 0, we'll be putting those values later, plus x over 1 factorial. Now the first derivative of sine is going to be cosine. So cosine x, and then we set x to 0 later, and we'll put that value later. Then in the third case, we have x squared over 2 factorial, and the derivative of the double derivative of sine is going to be, after the first derivative we obtain cosine, so we just take the derivative of the previous term, so that's easier in this case. So cosine's derivative is negative of sine, so minus sine x, then we set x to 0, and we continue like that. We have x cube over 3 factorial minus cosine x, which is the derivative of this previous term that we obtained over here, and then we set that x to 0. Then we'll drag it to the x to the power 4 term, then we can put the dots, and the derivative of the previous term is going to give me sine x, and then again we set x to 0, and then we follow it up with the extended series. Now this is going to result as sine 0 is 0 plus x over 1 factorial is 1. Cosine x, when x is set to 0, is equal to cosine of 0, which is equal to 1. So x divided by 1 multiplied to 1 is only going to give us x. In the third case, we have sine x. Now again, putting x to 0, that entire term goes to 0, so the third term vanishes. In the fourth term, however, we have cosine x, which again is set to 0 to give us cosine 0, which is equal to 1. But there's a negative sign over there, so we have negative of x cube over 3 factorial. Then again, the fourth term is going to vanish, and if you can guess it correctly, then the fifth term will be x to the power 5 factorial, but that will be positive because the sign in x to the power 4 was positive. Then again we would have had negative, and then we'll be getting the positive x to the power 7 over 7 factorial. So the odd terms with alternating positive and negative signs. So what we have the sine series as, the sine x value extends as the Taylor expansion of the sine series is x minus x cube over 3 factorial, then plus x raised to the power 5 over 5 factorial minus x raised to the power 7 over 7 factorial, and it carries on like that. So this is the sine series, the Taylor expansion of the sine series. Similarly, you can obtain the cosine, the tangent, and all the terms that you can think of. We'll take some other examples apart from these trigonometric series. We'll take the exponential case. So if we were to determine the expansion, the Taylor series expansion of fx equal to e raised to the power x, then we'll proceed in the similar manner where we have the first term as e raised to the power 0. Then we follow it up with x over 1 factorial. The first derivative of e to the power x is e to the power x for sure, and we have to set that to 0, that is x to 0. Then the second term has x squared over 2 factorial. The derivative again is going to be e to the power x, and we set x to 0 once again. So we continue like this with all the terms. We drop it over here, and then we write down the values that we get for e to the power x. We can write them directly. It's pretty straightforward. As you can see from here, the first term is 1 followed by x, then every x powered term set to 0. Remember, we are only setting those 0 values to the derivative terms. That is what I have mentioned right at the top over here, because the t is equal to 0 is only for those derivative containing terms. The term that is remaining outside, that is 1 over m factorial and even x raised to the power some power terms of x, that is going to stay as it is. The value or the setting of x is equal to 0 or the independent term to 0 is only on the derivative case, only applied to the derivatives. So e to the power 0 in each case is going to give us 1, and the rest of the terms are to remain as such. So we have x cubed over 3 factorial, and it carries on and on. So this is the extension or the expansion of e to the power x. In general, we can give the representation from 0 to some infinite value as simply x to the power n over n factorial. So this is the expansion of the exponential term in the Taylor series. We can consider a few more examples, one of the cases being the reciprocal of 1 minus x. We'll see how that unfolds. So if we are taking fx as 1 over 1 minus x, now most cases this x value has to be, in case this value of x is less than 1, then we'll have a proper value to this. But in general, we can observe this as the Taylor expansion will provide us with the following results. In the first term, we set x to 0, and we have 1 over 1 minus 0. And for the second term, again x over 1 factorial. Now because we are taking the derivative and this is 1 minus of x, so this is in the reciprocal term, so this is minus 1 minus x raised to the power minus 1 minus 1, which gives us 1 over 1 minus x squared. And because we are doing the derivative with respect to x, so and x is in negative, so we have a minus 1 again multiplied to that. Then as for the second derivative, we have x squared over 2 factorial. Now minus 1 minus 2, and again we have 1 minus x cube. And similarly for x cube over 3 factorial, the fourth term, that is minus 1 minus 2 minus 3 with the derivatives taken, and this is 1 minus x raised to the power 4. But we will also have a minus 1 over here because we are taking the derivative with respect to the x, which is negative in this case. So a minus 1 there as well. And since we are setting the value of x to be 0 in the derivative cases, so we end up with 1 plus x squared plus x cubed and all of that, which is the Taylor series expansion for 1 over 1 minus x. In general, we have this as the summation of x raised to the power n. Conversely, if we were to write the summation of x raised to the power n, we have the value as 1 over 1 minus x. So it comes pretty handy in all sorts of calculations that we do. A few more examples with the logarithmic case being equal to infinity for x is equal to 0, as we can see over there, and also for fx is equal to 1 minus x times x to the raised to the power alpha, some value, constant value alpha. Then we have the series to be a combination alpha cn minus 1 raised to the power n multiplied to x to the power n. So this is how we proceed as the Taylor series expansion of a few terms or few functions that we have come across. Now, up until now, we were expanding the given function about x is equal to 0. What if I tell you that we can expand about any other value? Say we are taking at x is equal to x0. So if we consider the expansion about x is equal to x0, where x0 obviously is not equal to 0 in this case, then we'll have another generalized case where we are taking the function as x plus x0. When it was 0, it was simply x plus 0, so we had fx. But now it's about the point x0, so that is added to the function. And the Taylor series expansion in that case is going to end up as n taken from the summation of n taken from 0 to infinity x to the power n over n factorial. That's okay. But the derivative, the nth order derivative of the given function will be about x0. So now that we were taking these cases as x is equal to 0 over here, so every derivative was having x is equal to 0 because the derivative was about the value x is equal to 0. Now with the expansion about x is equal to x0, we will be having this sort of a case. x0 is any point that can be considered or any value that can be considered as per the situation. So if we are taking the Taylor series expansion, then we take the derivative and we simply put the value x0 in all those derivative terms containing x, like we were doing for x is equal to 0, we will be doing for x is equal to x0 in this case. Also, we were considering till now a single variable function. What about the case of a two variable function? So if we are considering a two variable function, how are we going to get the Taylor series expansion for that? So if we have fxy, then the coefficients will now be depending on two values, that is m and n. So cnm x raised to the power n, y raised to the power m. This is the expansion, and the coefficients can be calculated for the values that we have in the Taylor series as follows. That is fxy is going to be equal to f. First up we have f00 for the values of x and y to be 0, and then we have the 1 factorials where we are taking x over 1 factorial and the partial derivative, in this case the partial derivative of f with respect to x at 0 0. Then the partial derivative, the y over 1 factorial and the partial derivative of f with respect to y, again taken at 0 0 points. That is x is equal to 0 and y is equal to 0. And as for the 2 factorial cases, that is x squared over 2 factorial, the double partial derivative or the second order partial derivative of f with respect to x, followed by y squared over 2 factorial, second order partial derivative of f with respect to y, not x but y, and again that is for the points 0, 0. Remember that we will be having some value x may be multiplied to the value of y in that given function, and correspondingly we will be putting zeros after taking the derivative on those derivative terms. But also here we have to consider a combination of both, that is xy over 2 factorial del square f del x del y, and then take the derivative, partial derivative, and set them to 0, the values of x and y, and it continues so on. So this is an extended form, or you may take it as the double function or the double variable dependent function. And further considering it, now these were about the point 0, 0. Like in the previous case, I mentioned that if we are taking the expansion about a point, that is, say x is equal to x naught, here also we can take the expansion supposedly about x naught comma y naught. Then we will have f for x plus x naught, y plus y naught. This is going to be the expansion, and what we are going to get is f x naught y naught. The first term is always the simplest one, followed by the more complex terms, that is the partial derivative with, well, if you have got the idea in the first case, in this case it's completely the same, except for the fact that the points are not going to be 0, 0 over here. You simply have x naught and y naught over here for those derivative terms. So we will be obtaining the same case as above. It will be same as above, the form that is, but we'll be having for x naught and y naught instead of those 0, 0 terms. So I'm just skipping it for the moment. I hope you understand that. Now, an important case to consider, to note down over here, is that an infinite series always goes to 0 as n tends to infinity whenever we have the value of x, the modulus of x, to be less than 1. That is, x is smaller than a certain critical value, which in turn is called the radius of convergence. Now we'll be considering the case where Taylor expansion doesn't really help us in determining a few values. Now, if we are considering supposedly a particle moving, and it was at rest till time t is equal to t0, and then it starts moving all of a sudden with a velocity, with a constant velocity, suppose. So we have the condition as xt to be equal to, it was x0 for t less than or equal to t0. So up until the time t0 it hadn't moved any bit, but thereafter it has moved, and it has traveled with a velocity v after the time t is equal to t0. So in some time t which is greater than t0, it will be t minus t naught. Let me write that clearly, it's a bit messy. So after that time it has traveled a distance, extra distance, that is v times of t minus t naught. Now, as per Taylor's expansion, only c naught is equal to x naught that will exist. But it differs from the given condition, with the reason being that the above equation changes its character at t is equal to t naught, because after t naught it has acquired a certain velocity. So the equation is changing character at that point of time, and the above given function therefore is said not to be an analytic at the point t is equal to t0. That means you cannot analyze the given function about that time where the function changes its character. So a change in character for a given function doesn't really help with the Taylor series expansion. Also, we have a certain series that we can consider. Let us take the case where suppose this is the first case. Let us take suppose another case where x of t is equal to 1 over t. Now this can't be used, the Taylor series expansion, because as you can see, if we are expanding it, we are getting 1 over 0 plus t over 1 factorial minus 1 over t squared, just like the case of the logarithmic series that we saw over there. So this thing over here goes to infinity, and that's not really yielding any result. So as a result, you're going to get an infinite case over here about the time t is equal to 0. Again, we can consider one more case where we are taking suppose x of t as root over of t. So t under root is going to be expanded like this, where we have t over 1 factorial. The very first derivative is going to give us 1 over 2 root t at t is equal to 0, and that's going to go to infinity. So that well, yes, we are putting the value in the derivative term, so that definitely goes to infinity, and we need not be concerned about the rest of the terms, and we simply are going to get an infinite result over here, an undefined result over here as well. So these are some of the cases where Taylor series expansion doesn't really help, or doesn't really give or yield any result, so as to speak. However, we can consider a few applications of the Taylor series expansion, but that will be in the next video in this segment. Till then, thank you for watching.